In this session, I would like to talk about communication between the processor and I/O devices. We know one thing: when you write a program, that program has to take the input and it has to give the output, right? So that's why I/O devices are required. That means input devices which gives input and output devices which gets output, correct? That's all part of the program execution, right? Otherwise, so the programs really require taking the input and giving the output. That's quite obvious. Now the question: when you are writing a low level program, let's say you are directly writing assembly level program, then you know how to do computations like addition, subtractions and multiplications. We have circuits, correct? Now the question is how you take the input from the keyboard, otherwise whatever the IO device, okay, and how you output it into the onto the monitor, right? This is a problem. For that, you should understand how IO devices can be, processed, otherwise, communicated. We will see that aspect today. Now, one more thing, we are not designing, otherwise, we are not seeing the low level details of how these IO devices are connected to the processor. That's a separate story. We will see that later. Here, we will be seeing programmer's perspective. That means being a programmer, how to access the IO devices, do we have commands, and what is the mechanism generally is incorporated. Okay, so we will see that basics of IO we will be seeing now. First of all, this is a picture you should understand. So you have a processor, you know that you have some memory. So far we just have written instructions such a way that the data was taken from memory and again calculations took place. After that we kept that data into the memory back, right? That was the thing we did, and we had instructions for that, correct? So we have studied them in addressing modes. That part is done. Now we will be focusing on this IO devices. You have, let's say, IO devices, they are also connected to processor and memory through interconnection network. Assume that, let's say, you have a network or cables through your processor, memory, IO devices, everything is connected. Now the interesting question here, first one is how you can access them is the question, correct? To access them, first of all, we have to give them some addresses, right? Like how you accessed memory, recall. So when you have memory, you access that memory through addresses, right? Memory, we just gave the addresses to memory. Similarly, for IO devices also, we can give the addresses so that we can access them. How we will see? Generally, what happens is, see here, example, let's say you have keyboard, okay? So in this keyboard, you have a key A like this. This is your keyboard. What happens is, generally in most of the architectures, every IO device is connected to one register, okay? So let us call it as keyboard register. Now whenever you enter this key here, that means whenever you type key A, then what is going to happen is the corresponding ASCII code of A. Let us take that ASCII code as 10110011. I'm not sure whether it is ASCII code of A or not. Just for time being, we are assuming that. So the ASCII code of A, let's say 10110011. Then what is going to happen is 10110011 will be transferred to this keyboard register. Such a way this keyboard will be designed. Okay. So now problem is reduced to how this ASCII code of A will be taken by processor. For that we have to write a program. How to write a program? See, one more thing here, we are all here worrying about how to write programs which access IO devices. That's it. That is the story. So for that we are learning so many details. Now this register has to be accessed. Now recall, is it the first time we are accessing the register? No, already we have seen how to access memory registers, correct? In the same way, you can access keyboard registers also. Okay. Now the problem is, our interesting question is, how IO devices can be accessed. Okay, how IO devices are addressed. Okay, that is one important question, right? So we will see there are two ways we can address the IO devices. One is here memory mapped IO, second one isolated IO. I will teach one by one. First of all, we focus on memory mapped IO. Memory mapped IO is one of the organization where what we are going to do is we are going to give addresses to the same addresses like memory addresses to keyboard registers. That means we feel that keyboard register is also part of main memory. If it is part of main memory, how you give the address in the same way we are going to give. Otherwise, I can say the addresses are going to be shared between memory and IO devices. Okay. Example, let's say you have 4 IO devices, I1, I2, I3, I4, and I'm assuming that there are 4 dedicated registers for that IO devices. Okay. These are the 4 registers. Now for simplicity, we have, let's say, 4 memory registers in main memory. So you might think that it's so funny, right? But just for time being, so that calculations will be easy for me, I am taking only 4 registers. General case is different. Now 4 plus 1, 5, 6, 7, 8. You have now 8 registers. Now if you address like this 000, 001, 001, 001, 100, 101, 110, 110, then we say that we are sharing the addresses, all possible addresses, to memory and IO devices, correct? Then that kind of model is called memory mapped IO. The advantage of this memory mapped IO is now there is no difference between memory and IO device, right? All are accessible or addressable elements. Now you can access IO devices also like memory. That means the same old instructions. Did you remember? Example, you want to load some data from memory to processor register. How could you write it? Then you can write like this: load some into register R1 where some data in the address 100, otherwise 100. When you write this one here, 100 is nothing but memory address. Okay, sorry, address. So now when you write it, then what was your expectation? Whatever may be the address, it is, you are thinking that it's a memory address. Go to that memory address, there will be some data and load that into R1, right? That is what the idea. So we can implement, otherwise we can extend the same idea. So rather than here memory address, it is a IO address, right? That means device address. Not a problem. It is also one of the register. Example, let's say this is a register related to keyboard and now current data is A. Then if you write load R1 100, what happens? So R1 gets that A. A means here ASCII code of A. Such a way we can plan. That is called memory mapped IO. The advantage of that model is you are treating all the registers, main memory registers and device registers as same, so that same old instructions like load, store, everything will work, so that your instruction set architecture, otherwise your instruction set design will become easy, right? So that is a flexibility you get. That's why people generally prefer memory mapped IO. There is an alternative way of addressing the devices, that is isolated IO. In isolated IO, what is going to happen is, example, let's say you have 4 registers in main memory. These are all, let's say, IO device registers. Okay, 1, 2, 3, 4. So in this model, we will be giving only 2 bits for these 4 registers. How you see 0001 1011. Sir, what about these registers, sir? So we can give again 0001 1011. Now processor should be intelligent. We have to plan our processor such a way that, so whether it is memory address or IO address, such a way your processor should understood. Okay, so how processor can be designed, we will see now. When duplicate addresses are possible, then we have to change our instructions. Example, to access the memory, you have instructions, right? Example, let's say there is a load instruction, correct? Load into register R1 a memory location 00. Let us give this to, because now this instruction won't work because 00 confusion, right? Whether it is memory or IO device, there is a confusion, right? In isolated IO, we will be giving separate addresses and we will be taking separate instructions. Let us use load in. Okay, that means load IO. This will be a typical instruction which is alternative to load. Okay, example, try to understand. Load IO R1 00. That means this is a different instruction than this one. Then your processor understand that this is a IO instruction. In that way, we have to implement IO instructions separately in this model, right? Otherwise, some other stuff we have to do, so that there will not be any problem. Now, when you have different instructions for IO devices and memory separately, then what happens? Complexity will be increased, correct? Then your circuit complexity will be increased. You remember it. More instructions means more complexity. Less number of instructions. And remember one thing, when your instructions are reused, Okay, your instructions are working for multiple tasks, that like accessing the memory and accessing the IO devices with the same instruction. That is simple design, but here it's a complicated design, correct? So when you have a complicated design, then it will become inefficient. That's why so people think that isolated IO generally is a complex organization. That's enough for you. Okay, remember, in memory mapped IO we share the addresses to memory and IO devices. In isolated IO, we give separate addresses to IO devices, so that we need separate instructions for IO and memory. I can say memory separately, correct? Now we will see how this keyboard's data can be taken. Okay, so for you assume that you have keyboard and keyboard has data, and data is already in the register and you accessed, right? But that's not the real story. The real story is user is going to enter the data and processor has to take the data. Such a way you have to write a program. Now we are going to think about a program. What is that program? User is going to enter the data, we have to take that data and we have to store it in some memory, and the memory addresses you can fix whatever you want. Okay, that is what the program. We are going to think about a program now. Let us start thinking. You understood the basic idea of devices, right? How devices are going to be accessed because of your memory mapped IO organization. What is going to happen? This is your keyboard, so this is your register, and whenever a user enters key like A or B or whatever, then that A or B, from now onwards I don't use ASCII, I use directly these symbols A, B. It will be easy for us to understand, correct? Okay, whenever user enters A will come. Then whenever user enters B, then this part will be erased and B will come, right? Now the question is how to take data properly. That means example, user enters data first A, then B, then A is going to B is going to erase A. Before that we have to take the data, correct? Such a way we have to write a program. Now we will see. So first of all, tell me one instruction to take the data. It is assume that let's say this IO device name is something, let's call IR1, IO device R1. Okay, IR1. Tell me how to take the data. It's very easy. Load into, first of all, load that into register R2, and this is IR1, right? Treat it as a memory name. Okay, so if it is memory, then how you take the data from this IR1? Load data from here into IR1. If really you have data here A, then happily A will come to R2. Later we can write this one, store, which is in R2, recall. After load instruction, really you have data here, then store instruction is going to store the data which is in R2. What is the instruction for that? Store the data which is in R2 into some memory location. Our program's purpose is, let's say this is some location which is predefined. I mean, through our program we will be defining a variable location. So location is a memory address, let's call 100 or something. Then we will be storing R2 location. Okay, then what happens? Definitely the data which is in R2 will be stored in this location. In that way we can continue, right? So next time also, if you have another character, then repeat these instructions. That's it. But the problem here is, when are you going to assured that there is a data, correct? Now how you write, when you write this program and directly if you execute, by that time user may not be ready, correct? Think about it. Let's say 9 o'clock, already assume that let's say you have written this program, okay, only 2 lines. For simplicity, assume that you have only 2 instructions. Whenever these 2 instructions are executed, then the data from the keyboard's register can be taken and it will be stored here. But here we are assuming lot of details. One important thing you are assuming is there is a data, right? Now see the story. Example, let's say you just started executing your program at 9 o'clock. When you said, my dear processor, please execute my instructions, then your processor will quickly come and it will execute these 2 instructions. But at that time, what if user is not ready to give the data, right? Then we should wait for the user's response, isn't it? Such a way we have to write a program. That's why this program won't work. What happens, I will tell you. Let's say user is also ready but not so ready, otherwise he is not as fast as your processor. Okay, now user thought I give data, processor also thought user is going to give the data. Example, let's say user is going to give data at 9 o'clock 1 second, but processor is executing the program at 9 o'clock. Will it work? It won't work, correct? That's why there should be a communication between this user and this program, correct? Program should be designed such a way that the user's problem should be understood. CPU speed is very fast, but this user is little bit slow, not little bit, very slow, but still we have to take the data from the user. So we say that, let's say this user or device is slow, correct? Why device is slow? Because it is going to be operated through user, correct? Now what we have to do is we have to ensure that there is really data here. For that we use one important bit called in bit. Let's say this one is keyboard in, okay, k in. That means what? Input is ready. So whenever this KIN bit is 1, then only there is a data. Then your program, whoever, we have to write a program such a way that that program should see this bit. If this bit is 1, then only we have to take the data, such a way we have to plan, correct? Now we will see that details, okay? So whatever the idea so far you learned, that is actually program driven IO, because we are writing a program to drive the IO. That means to know when data is available, right? So that's why this method is called program driven IO. In the program driven IO, so we will be doing this one. There will be a bit called KIN, okay? That KIN will be initially 0, and you will be having a circuit which is, let's say, keyboard circuit. Then you will be having this keyboard, I can say. Of course, circuit is part of keyboard. Now whenever a user enters a key like this, whenever he types A, then this circuit will process that response, and circuit is going to send the corresponding code to this register. Already we explained that, correct? Now when data is available, immediately this KIN bit will become 1. Such a way circuit is designed. Okay, that is not our story. What is it? Our story? Our story is how to write a program such a way that this data's availability can be checked. Simple. Simply write your instruction such a way that this bit should be transferred. First of all, take your CPU register, let's say R1. Write a program such a way that always you read this bit into here. Yes, such instruction we can write. Then whenever that bit is 1, then do that load comma store, which already I explained earlier, right? Okay. If this bit is 0, then go to the loop again. Do the same thing. Again, after again you take this bit, again you check. In that way, continuously you take this bit. Then some students will have this doubt. Sir, if this bit is 0, then why continuously we have to take that bit? Only one time I take and I repeatedly observe. Is that the idea? No. Because if you take always this 0, then you are always observing the old data and fixed data, that will be always 0, and you will be in infinite loop. It's not like that. Read the data, then check that one whether it is 0 or 1. If it is 1, do load and store and complete the operations. Otherwise, if it is not 0, if it is 0, then again go to KIN and check, because this keyboard, whenever user really enters the data, by that time when data is available, then this KIN bit is going to become 1, right, after some time. Meanwhile, we will be in loop, correct? So such a program we have to write. When you do that, then this process is called polling. Polling is nothing but observing one bit continuously. Okay, so generally we use a keyword called polling. That means we are busily waiting for something to happen. What is that? Data to come, right? So that process is called polling. So here your processor is checking 0, right? Always this bit, whether data is available or not. After that, in next instruction again you are checking. Next instruction again you are checking until really data is available, correct? This process is polling. Now the problem with polling I will tell you. Example, generally once data is available, forget about availability of data. Assume that data is available. Once data is available, then after all 2 instructions are enough to complete the process. But by that time, so assume that let's say load instruction takes 1 nanosecond of time. This store also takes 1 nanosecond of time. But user takes 1 millisecond of time. Then what are you doing? You see, your processor is seriously busy 1 millisecond of time doing nothing, because if data is not available, so this is unnecessary, right? Correct? So unnecessarily you are waiting on this slow user. So to get the advantage of multi-programming, that means if you design better program so that processor can at that time, example I can say like this, 1 millisecond of time you have to do polling, then 2 nanoseconds of time you will be really doing the right logic, correct? But sir, why to wait for 1 millisecond? But how do I know that when data is going to come? I don't know, right? In this model, in program driven IO, through the program I have to check whether data available or not. That's why what I am doing, constantly polling, right? So in this model definitely there will be such delay. Of course it's a bad design. We are not going nowadays, no one will do like this, correct? Program driven IO, you can understand, for just 2 nanoseconds of time is fruitful work, but 1 millisecond of time unnecessarily you are waiting on that user, correct? How to avoid that? For that we have a concept called interrupts. So because of interrupts, I will tell you what is interrupt. So interrupt is a kind of signal. So because of that interrupt mechanism, then this polling can be avoided, and we don't do program driven IO, so that your CPU can be effectively utilized. Okay, in OS also you study the same stuff, but these two are related. Okay. So finally, to avoid this program driven IO, that means the problems with program driven IO, what is that? Polling, right? Unnecessarily your CPU is wasting its time, correct? So see the ratio, how many 1 millisecond equal to how many nanoseconds? Think about it. 1 millisecond equal to 10 to the power of 6 nanoseconds actually. So 10 to the power of 6, your computer can do one operation in 1 nanosecond. Then in 10 to the power of 6 nanoseconds, how many operations it can do, like addition, subtractions and moving data from register to memory, everything? 10 to the power of 6, correct? Then that means what? 10 to the power of instructions execution time you are wasting, correct? Somehow assume that, let's say God is helping you. Okay, God and processor are friends. So somehow God is going to inform processor, my dear processor, now data is available somehow. In that way, if there is a communication, then is it not good? Then we don't wait, we don't do polling. Directly whenever God says that data is available, then only I execute these two instructions, and I don't execute unnecessary loop for 10 to the power of 1 millisecond of time, otherwise 10 to the power of 6 nanoseconds of time, correct? So that is what our target, but we don't have God's help, right? So how to replace this God's help? Do we have any other idea? That is interrupt driven IO. So in interrupt driven IO, what are we going to do is, we are going to use the help of hardware. That means hardware is going to inform us when data is ready, okay, through a mechanism called interrupts. We will see that interrupt driven IO. Example, I will give you an analogy. So let's say you are in restaurant, okay, this is you, and you want to eat some food, okay, maybe you want to eat some pizza, and this is the person who is making that pizza, okay, forget about this entire thing. So it's a restaurant. In the restaurant you want to eat pizza, you ordered. What is your main idea is not to wait, yeah? Just you want to eat some pizza and you want to go, okay. So to eat pizza it takes only 1 minute of time for you because you are damn hungry, but the pizza maker is taking 1 hour of time, let us say. That is a model. Let's say we are same thing, right? Here also keyboard is giving the data after 1 hour, right? It's taking 1 hour if you compare with the processor. Now what is the idea how you do the things here? Example, in restaurant, how you eat pizza? You will go to Pizza Hut or anywhere, sit and order. After giving the order, let's say after 1 hour you get the pizza. Then that 1 hour, what are you going to do? Generally assume that, let's say in hypothetical situation, you don't have mobile, you don't have anything. Then one thing, some of the people do this, they will constantly observe this maker, like he will be seriously seeing him, and mistakenly if this pizza maker sees him, then he will ask what happened to my pizza, when I will get, in that way. Otherwise for every 1 minute, so this fellow is going to this place, and he will just observe whether his pizza is available or not, correct? That is what we do, polling, correct? For every 5 minutes we go and we ask, what about our pizza? Is it ready? What is the status? Everything, right? That is one model. The second model, what we can do is, we can say like this: my dear pizza maker, you make a pizza, but why should I wait for 1 hour? Do we have any better mechanism? Can we have? Yeah, let us have an understanding. So I will be, you just call me, I will sleep. Okay. So he is going to sleep. Otherwise he is going to do some other work. Okay. So there will be a bell, that is interrupt. Assume that there is only one person here and only one maker. Okay. Only one pizza maker, one person to eat. If that is the case, then so the understanding will be like this. So pizza maker and user is going to have, that eater is going to have this I mean understanding. Whenever pizza is ready, then he is going to alarm. That means he is going to buzz this buzzer. When this buzzer is on, then this whoever wants to, I mean, let's call him Raju. This Raju is going to that pizza maker and he is going to get the date, I mean that pizza. That's the idea. Is it not good? So here he is happily sleeping. Otherwise, assume that let's say he has a mobile. Then happily he can watch some movie, right, in 1 hour. Then he is not wasting his time, right? So when he has some other work, then definitely this will be the best model. That's why, so interrupts are good when a processor can do some other stuff other than polling, right? If there is no work for CPU, then so however he is not doing anything, then there is no problem with polling. But one thing, your computers nowadays are designed such a way that multiple programs can be executed, right? So operating system, that's why now OS comes into the picture, of course. Okay. So what OS can do is, whenever some process, like here someone is going for IO, right? This is called IO. Whenever there is IO waiting for any process, then your OS can block such process and it can execute another programs. That's a separate story, we will see that. But here we are seeing hardware perspective, otherwise computer organization perspective. Forget about OS and everything, because that will mess up the things. We will see the link between OS and this computer organization later. At this moment I would like to say that your processor will be unnecessarily wasting its cycles by polling, correct? Rather than polling, if we have any better idea, the better idea is device interrupting us whenever the data is ready, correct? So don't ask, I mean, you ask yourself like what your processor is doing by that time. Maybe it can execute other programs, correct? In that way, so that you can think about like that, right? So that's why interrupts are really required, correct? So now we will slowly develop the idea about interrupt. So again, one more thing, sir, you are not teaching us any circuit related to interrupt, like how interrupt will be created, like how interrupts will be, multiple interrupts are created, everything. Here in this session, my idea is to teach you the programmer's perspective. That means how to use these interrupts, okay, but not how to create interrupts, otherwise how to understand the circuits behind interrupts. That we will be seeing in IO organization later, but here our class intervention is only explaining you basics first. But definitely I will teach you the circuits related to interrupts. At this moment, the high idea we will see.